webinar with the title of Gentle and Wide Probes for Super Resolution Mitochondrial Imaging. My name is Anna Fehir, and I am a product application specialist at Confocal NL, and I will be your host today. Before we get started, I'm going to go through some details. So we have a chat panel that you can find on the right side of your screen. Please feel free to use the chat panel to address your questions. And with Peter Drent, who is the co-founder of the company and also the sales and marketing manager, we try to answer all your questions there. This webinar is recorded, and after the webinar, you will get a follow-up email with the link where you can access the recorded webinar. We will start the presentation. As you can see the agenda. We will start the presentation from Dr. Zhixing Chen, and he will talk about the PK mito dyes using for bioimaging. After that, Jeroen Kohle will present the fundamentals of the NL5 technology and also the applications, and then give a live demonstration of the NL5 with living cells. And after that, we will have a Q&A section where we will answer all your questions. And now, first, I would like to welcome Dr. Chen as the first speaker, who is an assistant professor at Peking University. Dr. Chen is a chemist with research experience spanning including natural product synthesis, fluorescence, and nonlinear optical probes, and live cell imaging. His current focus is to develop small and micromolecular tools for advanced imaging technologies. I hope you are ready for the first speaker. And Dr. Chen, I will proceed to you.
Okay, thank you, Anna, for the kind introduction. So I'm Zhixing, now in Beijing. It's already evening, but it's afternoon in Amsterdam. So I'm very happy today that I can work together with Confocal NL. Together we introduce our dye, PK mito. We wish this dye can bring new dimensions for mitochondrial imaging. So it's my time to share my screen. Let me just share my screen. Okay. So can everyone see my slides?
Yeah, we can see them. Thanks.
Okay. Okay. Just one sec. Let me briefly rearrange my desktop so that I can see the questions at the same time. Okay. So now I think we are on. Yes, great. So I'm Zhixing. I'm an assistant professor at Peking University. Today, I'm gonna tell everyone about our gentle and bright probes for mitochondrial imaging. So if we speak about bioimaging, it's actually a very interesting field to me because if you look at the history of bioimaging, it's actually two forces. Some of people develop the best instruments to push the boundary of bioimaging, while the other half develop the probes. Only if these two parties join force, then can we push the boundary of bioimaging. So if I have always been thinking what would be the future of bioimaging, but if we together look at the past, you see this clear trend that instrumental engineers and probe engineers, they are inspiring each other, and so every technology advance during the past have instrumental part as the same time the probe part. For example, 100 years ago, people have H&E stain. So at that time, the bright field imaging, the bright field microscope as cutting edge technology, but you also have H&E, the two magical stains that can highlight the tissue. So that was 100 years ago. Then after that, 20 years later, in 1940s, people began to have immunofluorescence. That's also a joint force between fluorescence microscopy and bioconjugation technology, that people are able to link a dye to antibodies. Then after that, gradually we have confocal and turf. They are the fluorescence microscopes which offer Z-sectioning. At the same time, we have better and better probes. We have sensors based on FRET principles. We have photostable dyes. We have different colors, and eventually we have green fluorescent protein that we can genetically encode, so which greatly expanded the bioimaging capacity. Then jump into the 2000s, super resolution imaging emerged. We have STAD, we have STORM, we have SIM, we have better and better confocal microscopes. At the same time, we have better and better dyes. They are extremely photostable. Some of the dyes blinks so that you can do single particle reconstruction. Also, we are not limited to green fluorescent protein. We have genetically targetable fluorophores using like halo tag or snap tag. You can target really bright organic dyes to the cells. So that's actually the cutting edge technology of today. But as a we do biotechnology, I constantly ask myself, what would be the future like in the field of bioimaging? So, and I myself is a chemist, so I have always been trying to push the boundary of bioimaging using a chemistry perspective. So, if I want to briefly mention my track record of academic training. So, I'm trained by synthetic chemistry, organic chemistry, and polymer chemistry. But at Columbia, where I did a PhD and a brief postdoc between 2009 and 2015, I mainly developed two technologies to use chemistry to push the boundary. One is the protein labeling technology called TMP tag, which we can label extremely bright and switchable fluorophores onto cellular proteins. The other is with Professor Wei Min, who actually invented nonlinear Raman microscopy called stimulated Raman microscopy. So this microscopy can offer you a lot of colors, more than fluorescence. We can do 10-color imaging because the Raman band is actually much narrower than fluorescence. But the probe part is mainly I develop a lot of probes specifically for Raman, so that we can have isotope labeled alkynes and nitriles. They are very narrow and they offer multiplexity. We can do up to 10-color imaging. So during my track record, I have always been not only developing new chemistry, but work together with microscopists so that we can really have the cutting edge probes. So I'm fortunate that in 2018, I started my own lab at Peking University. Then at that time, I was actively looking for new projects. So then the one issue come to my mind, that is the phototoxicity. Why I'm interested in this issue? Because I realized now people have been developing photostable dyes. They want to make sure the dye does not bleach itself. But another issue often overshadowed by photo bleaching is actually phototoxicity. That's a concern about whether the cell or any creature would they be healthy enough under light to withstand the strong light. Why that matters? Because when the microscopes become stronger and stronger, the resolution becomes finer and finer. Actually, it comes with a cost that the light has to be strong enough to capture enough information. For example, we know that the sunlight, the sunlight intensity is actually around 0.01 to 0.1 watts per centimeter square. For the simplest epifluorescence microscope, is actually 10 times stronger than sunlight. So the cell would not be healthy if you look at them strong enough. But with confocal microscope, STORM or STAD or the stimulated Raman scattering microscope I have been using, their lights are extremely strong. So to capture additional information. So I remember when I was a PhD student, I used SLS microscopes trying to capture a live cell. Maybe when I do 10 experiments, 5 times the cell got burned, while the other 5 times I got I got satisfactory images. But that's not really acceptable. So at that time, one day I suddenly remember when I was a boy, maybe at the age of 10, I used to use magnifier to burn ants. Then I realized, now I'm doing my PhD study. I'm essentially doing the same thing. I still use a strong light and focus it and to burn a living creature. So at that time, I begin to appreciate phototoxicity may be the next fundamental limit of bioimaging. So then the question is how to tackle it. So in 2018, I joined Peking University. I'm fortunate enough to work together with a brilliant microscopist, Professor Zhixing Chen. So at that time, he invented a new microscope called Zhixing Chen. Chen is basically a very mild confocal, very mild super resolution solution. So combining new optics and new algorithm, Professor Zhixing Chen is able to image a cell for more than 1,000 frames under super resolution, but still he encountered huge problem on phototoxicity. For example, this figure is telling you that when you look at the mitochondria, after maybe 10 or 50 images, the mitochondria becomes simply swelled, and they are no longer healthy. So indeed, we can capture a lot of information with this new microscope. But if the mitochondria is no longer healthy, then nothing makes sense anymore. So Professor Zhixing Chen challenged me whether we can use chemistry, using a chemistry point of view, also try to eliminate phototoxicity. And I think that's a very good direction. So Liang told me that his microscope is already very, very gentle among all the super resolution microscopes. Remember, the sunlight is like 0.1 watts per centimeter. His Zhixing Chen is like maybe down to 10 watts per centimeter. Then later I learned from Confocal NL. Later, Yaron will show you his microscope, the RCM microscope. It's almost pushed the boundary down to like a epifluorescence microscope. But still, so I want to show you that as physicists, constantly pushing the light to be lower and lower to make the cell healthier and healthier. But like a phototoxicity, the fundamental problem is just not only you need umbrellas to block sunlight. From a chemistry point of view, maybe we also need sunscreens to really shield, protect the cell in situ. So that became my first idea when I started my lab. So the question is, how can we come up with sunscreens to protect the cell under microscopes? So that's just an analogy because we are not literally making sunscreens because the phototoxicity is slightly different. So here is a chemistry principle of phototoxicity. If we look close, so the process is like this. A fluorophore used to stay at the ground state when it's excited by light. It jumps to the excited state, S1. The S1 state can either give a photon, that's a fluorescence, and jump back to the ground state, or it can undergo an unwanted intersystem crossing to triplet state. The triplet state is actually a long-lived dark state, which does not contribute to fluorescence. But triplet state, because it's both long-lived and reactive, so it can actually react with molecular oxygen to form singlet oxygen. Or the triplet state, being a biradical, can also undergo redox reactions to give a lot of other radicals. They are all reactive oxygen species. That's a really harmful and reactive. If this ROS hits the dye, and the dye they can decompose the dye, that's causing dye decomposition. That's photobleaching. If this ROS reacts with biomicromolecules, causing oxidative damages, then you see phototoxicity. So photobleaching and phototoxicity, they are connected, but they're not the same. One brilliant idea in this field is to use triplet state quenchers to react with triplet states, to bring the triplet states back onto the ground state, thereby eliminating triplet states and finally reducing ROS. So that's basically the popular solution in the field. So I want to acknowledge some prior arts. For example, Professor Scott Blanchard and Thorben Cordes, they spend a lot of time to work with this triplet state quenchers. So like Blanchard group proposed a strategy. They say, okay, if you link a triplet state quencher covalently or non-covalently to a fluorophore and make sure they are very close, then the triplet state quencher can directly heal the fluorophore when the fluorophore jump into excited triplet states. And in this, using this molecular device, these groups are able to study single molecule threat because they are single molecule biophysicists. They care about looking at a single molecule, looking at the proteins that are labeled, looking at the proteins that are labeled with better dyes. So they pioneered this field called self-healing dyes. But none of these biophysicists really appreciate cell biology, because actually this kind of TSQ conjugated dyes, when they conjugate to proteins and they do single molecule tracking, it's not much better than the solution added protective agents, because you can have maybe even like millimolar or 10 millimolar protective reagents in the buffer. But actually in live cell imaging, if you want a fluorophore to be protected inside the cell, there you have to use this covalent linking strategy. But at that time, before us, no one really considered using this strategy to do live cell imaging. So when I have my lab, we decided to test whether this strategy can work into the cell and alleviate the phototoxicity. So the first experiment we did is we conjugate 3 proven triplet state quenchers to classical dye size 3. So we picked Cholox, a vitamin E derivative, which is a reductant. Nitrobenzene is an oxidant, and cyclooctatetraene, this weird molecule, polyene molecule. So we conjugate these 3 molecules to size 3 and test their cell behavior. And then we figured that once we conjugate Cholox, it's no longer that cell permeable. So nitrobenzene and COT conjugates are reasonably cell permeable, and they give distinctive mitochondrial labeling pattern, which is encouraging. We went ahead to test the phototoxicity of the nitrobenzene size 3 and the COT linked to size 3. And we find that when size 3 conjugated to COT, the phototoxicity dramatically decreased. But when size 3 conjugated to nitrobenzene, it's equally phototoxic compared to the parental size 3 molecule. Oh, this is by cell apoptosis assay. One intriguing observation is here we want to emphasize that photobleaching does not equal to phototoxicity. For example, like the size 3 nitrobenzene conjugate, this dye is actually the most photostable compound in our hands, but nitrobenzene obviously does not offer alleviation to phototoxicity. But COT, once conjugated to size 3, is not that not that photostable, but that's the only effective triplet state quencher that eliminates the phototoxicity. So that's also an interesting point I want to mention. So encouraged by this result, we decided to further move forward to prepare the analogs. So we prepared 2 molecules. One is the size 3 biscot called PK metal red. The other is size 5 biscot named PK metal deep red. The good thing about these 2 dyes is they cover the red channel and the far right channel in typical microscopes. And then with this dyes, we want to compete with the classic reagents in this field called metal trackers. So metal trackers are developed by Molecular Probes. It's a very good company, eventually acquired, and now under Thermo Fisher. Everyone in the field, when you want to image mitochondria, you probably go to metal trackers. But these molecules are developed in like 30 years ago. Very good molecules, but they simply are very phototoxic. And the PK metal dyes, if we compare to the metal tracker red and deep red, they are much less phototoxic. So the cell viability goes goes much higher. So our dye really excel, outperform the classic dyes on the market. So here are some images you can see. On the left is the mitotracker DPRAD, labeled mitochondria and highlighted by red. So this is mitotracker. Here is PK metal DPRAD. If we look at the image, here is a 3D reconstruction. If you look at this one image, if you take a snapshot, then these two are equally good because they all highlight mitochondria very clearly. But if you want to reconstruct a time-lapse 3D imaging, then you see the difference. PK metal DPRAD, because too phototoxic, you can see after 7 3D volumes, the cardiomyocytes simply shrink. But PK metal DPRAD can withstand for up to 20 3D volume images. So it's like around 3 or 4 times offer 3 or 4 times longer imaging window compared to the mitotracker counterparts, both on the red channel and on the far right channel. And that's cardiomyocytes, that's primary cells, which are very valuable. Then we further move on with collaborating with Professor Zhixing Chen, testing our PK metals under his Zhixing microscopes. And here's the comparison. Here's mitotracker and here's PK metal. You see, after 200 frames, the mitochondria got swelled and basically the cell died after like 300 frames. But PK metal, our dye, under Zhixing, we can offer up to 2,000 frames at a rate of 10 frames per second. So this is this is the COS7 cells. If you image really long for like maybe more than 1,000 frames, inevitably you get some dye leaking onto the ER and the mitochondria gradually swelled. But again, here is we are comparing 2,000 frame imaging versus 200 frame imaging of the mitotracker counterparts. So I think that was very encouraging result, saying these the reduced phototoxicity can give you a lot of new information under the cutting edge super resolution microscopes. For example, before the mitochondria only swelled after a long period of time, but now you can catch a lot of fine movement of mitochondria, like this kind of tip extension and retraction, or you can see the dynamic protrusions of this inner membrane, because PK metal and the mitotracker, they both localize themselves onto the inner membrane of mitochondria, and you see a lot of dynamic events. Yeah. So last year we published this PK metal red and DPRAD on Chemical Science, and it's kind of very well received. We packaged our product and distributed around the world, and I think people are really happy with our dye. So for example, a barrier, I think everyone knows a barrier is the stat company started by Professor Stanton Hill. So they asked our dye, and here's their data. Under Confocal, you cannot really resolve Christie, but understand our PK metal orange can do up to 20 frames of stat imaging without obvious phototoxicity, and you can see it's crystal clear for more than 20 frames. So yeah, so that's basically the story about PK metal. We basically highlighted how simply by conjugating the cyclooctane tetraene, we can effectively deplete triplet states and inhibit all these ROS and use this concept to alleviate the phototoxicity. And I think we are the first group to demonstrate this concept of alleviated phototoxicity using chemical approaches inside lab cells. Yeah. Here I want to tell you another story, also working together with Professor Zhixing Chen, also to tackle phototoxicity, but with a brand new approach. And here is the problem. The problem is Professor Zhixing Chen has a system. He is interested in study islets, how how beta cells secrete insulin. When you want to image insulin, you can actually image the zinc cation, because they are secreted together. So when you use when they use the classic zinc dye called rho zinc 1, also from molecular probes, this dye is really sticky to the membrane. You see a lot of background signal, and gradually the cell is too toxic. The cell the cell just underwent apoptosis. So you cannot really authentically record all these secretion events. But so we jump in and we made a new version here, PK zinc red 1, and if you do the same assay, you see only this sparkle is just a beta cell secretion events, and you see the zinc release out. Here's the vesicle secretion, but you see no background and no phototoxicity. And here the trick is we fine-tune the molecule so that to make the molecule a little bit more hydrophilic, so that it's not sticky to the membrane, giving no background, giving really less unwanted stain, so that it can eliminate the phototoxicity and authentically record the secretion events. So here, basically, we proposed a new another technical route to eliminate phototoxicity. That is, we want to have the balanced polarity molecules, so that to minimize the membrane interaction and make sure it only stain the physiological events. By this way, we can minimize the loss and reduce the phototoxicity. And eventually, we not only have a red version of the zinc dye, we also developed a far red version of zinc dye, which because using silicon rhodamine as a scaffold. So with silicon rhodamine in hand, we now have a far red zinc dye. And remember, we have red metal dyes, so that here the green channel we can also at the same time use GChem to do calcium imaging. So altogether, we can do 4-color imaging now. Here is the isolated islet, and you can see how the insulin secretion colored in red by PK zinc far red 3. So these red dots are the secretion events, and the PK metal red colored in yellow here to indicate the mitochondria, and also the green channel is the GChem to tell you which beta cell is getting excited. So we have gigantic amount of data showing the correlation between mitochondrial content imaging, mitochondrial content and secretion at the same time calcium signal. So I think this video is very appealing, because it opens a new paradigm of doing islet imaging. That is, we can have multicolor imaging, and the observation is really long, for more than 10 minutes. Then we can fully capture the spatial temporal events inside the live islet. But all this recording is made possible by two optimized dye. That is PK metal red and PK zinc far red. They have really little phototoxicity, so that they can authentically tell you what's really happening inside the cell. And maybe you are interested in one question. If you look at this PK metal red staining in the live islet, some of the cells stain heavier, while the other cells do not stain very heavy. So the mitochondria signal has some difference across the cells. That's not a problem, because we also realized PK metal is not only indicating the mitochondrial structure, but the stain heavy or less mitochondrial signal also may have some biological significance. Here, that's a collaboration between us and Professor Kai Lei from Westlake University. Professor Lei is interested in a weird creature called planarian. This worm is extremely regenerative. That is, if you cut this into 10 pieces, 2 weeks later you get 10 worms. So Professor Lei isolated their stem cells, and he needed really mild reagents that can highlight mitochondria at the same time minimally perturbative to the stem cells. So he applied our PK-mito red to his pulmonary stem cells, and they do flow cytometry analysis and cell sorting to sort out. He found two different kind of cells. Some of the stem cells have lower mitochondrial signal. Some of the stem cells have higher mitochondrial signal. And actually, the lower mitochondrial signal group is the most regenerative ones. So I show this data to you because I want to highlight the biocompatibility of PK-mito red, not just under light. It's really biocompatible, so that it are also applicable to all kinds of primary cells for cell sorting purposes. So it can give you a lot of information in different dimensions, both under super resolution microscope, tell you the structure of mitochondria, but it can also give you some hint on the mitochondria activity. And the biology here, we are still working on it, but I just want to show you that the biocompatibility of this PK-mito red dye. Okay, so basically I told you one story on how we use like triplet state quenchers to eliminate phototoxicity, and how we use other molecular engineering strategy to reduce phototoxicity, and altogether our reagents can be used used in combination to give you maybe multicolor imaging. Okay, so last year, because people really love our PK-mito red, so we started a company called Confocal Tech in Nanjing, China. So it has been a year, and our product has been distributed to more than 50 labs worldwide, and yeah, so also that's why we came here together with Confocal NL. We are trying to work together to distribute our dye globally. So it's a very good opportunity. But if we come back to the very first question I asked, I'm constantly thinking, what's the future of bioimaging? And I think I have a tentative answer. I think with super resolution area, and now maybe in the future, like 20 years later, people will doing 4D super resolution imaging. That means you're not only doing 3D XYZ, and also the time, the time-lapse imaging is becoming increasingly important, so that you have full amount of data at super resolution and at multicolor. Maybe you also have so abundant data you have to rely on computer to analyze them. But the infrastructure of this trend is basically, I think, two things. One is we want to have really good instrument that has minimal phototoxicity. On the other hand, on the probe side, we want to have the dyes that are not only very photostable, very bright, but they must have really little phototoxicity to be compatible with this imaging in the 4D area. So like this video is done together between us and Confocal NL. Actually, Yerong got this beautiful video. You can see our mitochondria, the PK-mito combined with Confocal with RCM can offer you like hour-long images of mitochondrial dynamics. So I think that maybe this represents the future, that how instrument and probes bring together to push the boundary of bioimaging. That's pretty much all the story. So it's made possible for my collaborators and my hardworking students. And if you want to know more about my lab, you can come to my lab website. If you want to use PK-mito red or PK-mito deep red, you can either come to us or together with our strategic partner, Confocal NL. And that's it. I look forward to your questions and discussions. Thank you.
Thank you very much, Dr. Chen. Thank you for the very interesting presentation, and also for introducing the PK-mito dyes for us. It was amazing to see the remarkably low phototoxic effect of these probes on mitochondrial dynamics. I think that's a really important development, and I'm pretty sure that it will improve the imaging experience of the scientists.
Thank you, Anna.
I cannot see any questions at the moment, but I was wondering whether are you planning to develop dyes for other wavelengths?
Now we have two wavelengths. We have red and deep red. We tried really hard to make green work, but not successful yet because each dye has a brand new chemistry. We are still working on the green channel. Yeah, that's pretty much the answer.
Yeah, that's great. I think that the red and the deep red is very, very good, and as I used, they work very well. Yeah, I saw another questions, exactly. So the question is, in designing PK Mito Red, you choose a strategy in which the triplet is quenched. This requires both the fluorophore and the quencher. It should, in theory, also be possible to produce a fluorophore with a very low rate of intersystem crossing. Why was the strategy? Yeah.
Maybe you can finish. Yeah, other people will hear.
Yeah. So the question is, in the end, that why was the strategy that require both fluorophore and quencher chosen?
Okay, that's a very good question. So from a chemistry perspective, in theory, you can choose a dye of very low intersystem crossing. But in reality, signing dyes and rhodamine dyes, that's the most commonly used dyes for bioimaging. They already have a very low intersystem crossing. They have much lower phototoxicity than other dyes like fluorescein. So I think also maybe there are other structures having lower intersystem crossing, but these dyes will not be as bright as signing dyes. So signing dyes are really bright. If you multiply its extinction coefficient with their quantum yield, you get more than 50,000. So that's phenomenal. In theory, yes, maybe we can find some other dyes that are less phototoxic, but we do not want to sacrifice brightness because that's also because without brightness you cannot even have one frame of super resolution imaging. That's why we choose to start with signing dyes. I don't know if this answers your question, but that's a very good question.
I think so. I can see another question as well. Are PK mito dyes interfering with the mito function? For example, killing protein gradient or reducing their ATP production?
As far as we can see, it's minimally interfering. We did some cell viability assay, and up to maybe 1 millimolar, up to 10 micromolar, no problem. Yeah, that's pretty much the answer. It's kind of philosophical because when you want to image something, inevitably how to interact with that. It applies to all the probes. Like if you fuse a GFP to a protein, the protein is no longer the protein it used to be. If you image like tubulin with a taxol conjugate, that's also blocking the tubulin to some extent. But we did pretty much a lot of experiment. I think PK Mito Red is not that. Basically, we see no bad effect to cell. At least it's as good as metal trackers in terms of cell toxicity.
Okay, thank you very much again. And now I would proceed it to Jeroen because we are quite short in time. Jeroen is our next speaker, who is product manager of Confocal NL. Jeroen worked at the microscopy facility at Firth Medical Center for several years. And then he joined to Confocal NL in 2018, and he has extensive experience in microscopy and live cell imaging. Jeroen, are you ready?
Thank you, Anna. Let me know if you can hear me and if you can see my presentation.
Yes, we can.
Okay, cool. Thank you. So today I will talk about mitochondrial imaging using the NL5 fast confocal scanner. So the NL5 is is a product which we recently introduced about 2 months ago. And today I'm going to show you what it's useful for, how it works, and at the end I will demonstrate this system to you, including the nice and bright mitochondrial dyes from the Chen lab. So first, what is NL5? So you can see the product here. It's this box. This box couples to any inverted or upright fluorescent microscope, and it turns it into a fast confocal scanning system, ideal for deep 3D imaging of living samples. So what does it offer? It offers high resolution, 240 nanometers in the standard, in the raw data, and 170 nanometers in the deconvolved data. Very importantly, it offers high sensitivity using the latest SCMOS camera detectors, which go up to 95% efficiency. It offers a fast scanning speed of 25 frames per second, and it's very compact and easy to use. Actually, an excellent add-on to imaging facilities. In the coming slides, I will show the applications for which NL5 can be used. So for example, you can think about studying fast cell dynamics, such as cell migration, intra-extracellular transport, or cell signaling. Here you see a 3D time lapse in time of a HeLa cell which was stained for actin using LiveAct GFP, and you can see clearly these protrusions, extending to the outside of the extracellular space, and the cell is sensing where it should go to next. It's very interesting to watch. And here we recorded, thousands of images, and the cell was not harmed. We go to the next slide. Not sure if this video will work, but this will demonstrate an application in which the NL5 is used for really long-term imaging. I have it here as well, just as a video. So here you can see a zebrafish, which was stained for endothelial cells in green. And you can see the development of the zebrafish over a period of more than 24 hours. So you can see the cells moving around. You can see new blood vessels start to develop. And again, this is all not possible if you have an insensitive microscope. Okay, going back to the presentation. Okay. Also, NL5 is really useful for deep 3D imaging. So you can think about organoids, or the zebrafish I just showed you, or mouse embryos, or even 3D cultures within hydrogels. The nice thing about NL5 is that it uses a single pinhole to record the image, which is good because spinning disk microscopes, which is the counterpart of fast confocal scanning, have a disk of pinholes. And some people know that if you go deeper, you get crosstalk between the pinholes and therefore less image quality. So NL5 doesn't have this problem. Again, I need to switch to the video here. I'm sorry for that. We're talking about this one. So here you can see a Volvox where we imaged more than 90 micrometers inside, and you can see that we have the same image quality in the bottom as in the top. So there's little to no aberration. And that is great because this allows you to really study what's happening inside and not only what's happening at the cover slip. Now look at these fine lines that are now, 80 micrometers inside, even 90 micrometers. Okay. So here we see the difference of the NL5 performance versus a spinning disk microscope. So this is 20 micrometers inside the sample, In this case, image quality is more or less the same, but as mentioned, the pinhole crosstalk issue is when you start to go deeper in the sample. So here you see the same spot, but then 60 micrometers in. And then you see here, it's of course more blurry than on the left side. Also, we measured here the exposure light, the light intensity, and it turned out to be 0.8 for the NL5 to make this image, and 9.5 for the spinning disk microscope. So we have a factor of 12 difference here. So 12 times more intensity here compared to here, and that will make the difference when you do long-term lifestyle imaging. And this becomes, of course, even more apparent when you go more deeper into the sample. Here you see the effect of deconvolution. I'll also show that during the live demo. So we have an on-the-fly deconvolution tool that can improve the image quality further. And the final video will be about high content screening applications, where you want to quickly scan through a well in multiple colors and identify the most interesting wells. So we can actually do very fast color switching. A 4-color frame would take 400 milliseconds to acquire, and that means you'll be able to capture live cells in multicolor in 3D, and then be able to capture this nice mitosis here. I'll play it again. So we can see the tubulin, the actin, and finally the DNA, which decondenses into 2 individual nuclei. Okay, I'm coming back to the presentation here. So that brings me to the end of the presentation. I will now move over straight away to the demonstration of the NL5. Closing this. So the NL5, just like the RCM, can be operated from Micromanager. And Micromanager is an open source software that allows you to control any type of microscope, any camera, any laser. So that is very nice. You have one platform to use all these different microscopes. In terms of user interface, very briefly, we have a snap button here just to get one image, or the live button to get a stream of images from the camera. And here under multi-D acquisition, we can do the more complicated experiments like Z-stacks, multicolor, and time lapses. And then here on the right-hand side, we see the buttons, so the operation of the NL5. So we have a channel selection, so we can look at the sample in bypass mode. That means if the light is on, sorry for that. Yeah, now it should work. So you can use the bypass mode to find the sample in epifluorescent mode. Of course, epifluorescence is very blurry. So here we want to have the confocal capability. And in order to have that, we simply select the appropriate laser. In this case, it's the 561. We set the laser power and we go live. And we get a nice image. So here we have a nice and clean image of the sample. These are macrophages. The macrophages are stained with PK mito red. So it's a mitochondrial dye that Dr. Chen showed to you in the presentation, excited by the 561 laser. And I must say it's a very, very bright dye. So you only have to add a tiny amount. I added 0.2 microliter for a 1 ml volume. So 1 in 5,000 dilution, and I think you can even go further. And then I already get this very bright signal here. So now we can do some live 3D time-lapse experiment. So here we have a cell which is nicely spread out. So You can see the mitochondria moving over time. And what I will do is I will just take this cell out of the field of view, make a region of interest, and then we start doing a Z-stack here in time. So I will use the multi-dimensional tool and have to move around some windows and choose the top and bottom position. So this will be the bottom, and then we go to the top. So in this case, I have 73 slices. And I will save these images to the drive. And while they're being acquired, they're automatically being deconvolved. So this is something I could show you while this is actually acquiring, so you can see the data coming in. It's happening quite fast. I'm not using a piezo stage here, so it's a regular microscope focus, and that gives me 10 slices a second or something like that. And we can do that over time as well. So let's do 20 time points. Sounds good, reasonable. So it's acquiring it. Just let me change the lookup table to green. It's more appealing, I think. Yeah. And here the data is coming in deconvolved. So already now at the second time interval. And what I want to highlight here is that we don't have photo bleaching. We can image these cells for pretty much an indefinite period of time. And that allows us to extract much more data. So here I'm moving in the focus. Let me change the lookup table so that you can see all the fine detail there. And this cell is happily moving around. The mitochondria are fusing, they're splitting, so you can see that here, for example. Oops. And of course, we're acquiring a full 3D volume, so you can also see stuff happening at this level. It's maybe also time to compare some data. So if we say we want to compare the same XY slice and compare deconvolved versus raw, we will be looking at this. So here we have on the right side deconvolved, left side raw image, and of course you can clearly see that we have a much higher signal to noise ratio on the right hand side and improved resolution. So we make it easier to separate objects here and to perform subsequent analysis. So this is going on. I will share these data with you. You will receive an email in about 4 hours. And then you can, if you want, you can take a look with your favorite software and look at the image quality. Thank you very much.
Thank you very much, Jeroen. It was a really interesting presentation, and also it was good to see how fast the NL5 can scan the sample. Mm-hmm. Could you show us whether the NL5 can provide homogeneous light on the whole frame?
Yeah, sure.
Because it can be, I think, important.
Very good one.
Because sometimes, yeah.
So in that case, I'm stopping the acquisition here. That's okay. Yeah, so the illumination uniformity, that's one key parameter actually that needs to be taken into account. So I'll go back to the full view, seeing all the cells. So basically, we're talking about the same intensity in the center of the image as in the corners. So watch this cell here, this cell that we've been imaging, and I move that one to the corners of the image just to show you the evenness of the image. This is a manual stage, so it requires some precision. But you can see that the same intensity remains. So if I move the sample through the field of view, see that it has the same intensity in the center as in the sides. It's actually quantified, it's within 90%, so that will allow you to have better measurement of the sample. If you want to do quantitative measurements or stitching, then this is all possible. Yeah.
Thank you. Thank you very much, Jeroen. So I think
Jeroen, why not show a movie you took before, the very long stretch of mitochondrial movie?
I can show that here. So
yeah, why not?
Let me know if that's visible to you. So this was done on the same cell type, but using RCM. And RCM improves the resolution further than what NL5 does. So we get a resolution that is very similar to a Hessian sim, but with a very low laser intensity. Remember the first slide that Dr. Chen showed about laser intensities throughout microscopy? That is really a big difference. So you'll be able to do much longer experiments than what you used to.
Yeah, actually, I'm not able to see the video in China, but that's fine. Maybe if on a positive screen, that would be better.
Yeah. Okay.
Thank you very much. I cannot see any other questions here. Please, if you have any questions, you can address it in the chat panel. And I think as we experience the NL5 and the PK mito dyes can really prevent phototoxicity. And in a collaboration of the Chen Lab and the Confocal NL, now you can order the PK mito dyes from our website, which will open soon. So on the website, you can find the web shop page, and you can order the PK mito red and the PK mito deep red dyes soon. I think at most 2 weeks from now, we will open the web shop. So I would like to thank you for Dr. Chen and for Jeroen, your presentation. And it was, I think, really interesting, useful, and I could hear a lot of new information. So thank you very much for that. I would like to also thank you for Peter for taking care of the chat panel. But the special thanks is for the attendees who could have some time for us today. I really hope that you could hear some new things and you enjoyed the webinar as much as I did today. For more information, if we don't have other questions, do we? Jeroen?
I think that was it. Everyone
okay.
was very enthusiastic, and also thanks to you, Anna, for organizing it and for being the host. I think you did a good job. So
thank you.
Thank you.
For more information, you can visit our website, and also please follow us on social media. From the website, you can book a remote demo. And if you have any further questions, you can just address it to the sales@confocal.nl. Thank you very much.
Thank you. So there's one person that asked, is there a replay? Yes, it will be available. You will get a link in about 4 hours where you can watch the entire thing once more if you want.
Exactly.
Okay. Thank you very much.
Thank you.
Bye-bye.
Thank you all.
Bye. Take care.